Hi students. In this video we'll see what is cascade amplifier. So now we will take up a design to understand the requirement of cascade amplifier and try to understand the working of cascade amplifier by doing the simulation, and we try to understand what is the role of different stages of cascade amplifier in realizing the requirement. Okay, now the problem statement is you're asked to design a MOSFET amplifier stage to have a gain of 10 volt per volt for a resistive load of 100 ohm. So we have a load of 100 ohm, and we have to have MOSFET amplifier stage so where it will give a gain of 10. So now we can start with, because we know CS amplifier which can give a gain of 10. So now let us start with design of a CS amplifier with a gain of 10, and we will connect this load resistor of 100 ohm and try to find out what is the impact of connecting this RL to the amplifier and see what is the changes in the gain of the amplifier. So once we see the changes, suppose if that gives a huge reduction in the gain, so let us design a CD amplifier, that is common drain amplifier, and observe the overall gain by connecting this load resistor as the output for the CD amplifier. Now the input for the CD amplifier comes from the CS amplifier, and that is fed to CD amplifier, and whatever load that RL was connected to CS amplifier now will be moved to the load for CD amplifier. And then we try to see what is okay, let us redesign the value of redesign CS and CD amplifier stages put together so that we get a gain of 10 with a load of 100 ohm, with a load of 100 ohm. Okay, now let us start this process. So this is what we are doing here. So this is a CS amplifier. First stage is we are realizing a CS amplifier with some RD load. So now this RD is not 100 ohm. So let us consider a resistive load RD such that I will get a gain of 10. So that such that I'll get a gain of 10. So now we are now having some specifications like, okay, R1 is 200k, R2 is 100k, and RD is equal to 1k. So let us assume these as the dimensions of the MOSFET. Let us apply supply voltage of 1.8 volts. So let us assume these are the uh, model parameters of MOSFET, and from the equations we can write the gain of this MOSFET is given by minus GM into RD, where we got the expressions for GM as so and so, and we can actually find the value of ID, and with the known values of Kp and WL we got the gain of GM of 10 millisieverns. So ultimately we are getting a gain of minus 10 volt per volt, which is 20 dB magnitude. So this is upon having a RD of 1k, RD of 1k. Now that's what I have in my simulation also. So let me show you the simulation. Okay, I have cascaded it. So what I'll do is, let me just cut this here. Let me make this equal to 1k and try to find out what is the gain of this amplifier. So now let me save this and let me run this. So when I run, let me see what is just the gain over here. So I am not I'm interested in seeing the gain over here. So the gain here is, you can see now the gain is this is 20 dB. So you are getting a gain of 20 dB with RD as 1 kilo ohm. So we have not yet connected that 100 ohm resistor. So let us see, if I connect 100 ohm resistor, what is the gain that I want to get. So I'm doing a frequency response analysis. I'm trying to see what is the midband gain. So midband gain is 20 dB, which corresponds to okay, which corresponds to a gain of 10 volt per volt. So now let us go back to this and try to understand what is the effect of connecting RL to the amplifier having a gain of 10. So in the second stage, what I will do is I will connect this 100 ohm load to this amplifier, which is designed for a gain of 10. So now this is designed for a gain of 10 with RD is equal to 1K and R1, R2 and all these specifications done. So we have verified that it was giving a gain of 20. Now the moment I connect this 100 ohm as the load, you can see the AV expression reduces to RD parallel RL as the load, and of course the minus GM value. So now you can see the gain drastically reduces to 0.9, that is less than 1, which happens to be in dBs. So this is minus 820 7.89 milli dBs. So there's a huge reduction in the gain from 20 dB, it reduced to this much. So let us verify the same thing here. So now what I'll do, I will connect, I will simply connect this to this. Okay, let me have this connection from this to this. Let me also connect this 100 ohm to this. Let me open that connection for the time being, because let us see that after that. So now let me run again. If I run now, you can see the gain has reduced from, okay, if you can see this gain. So now let me just cut everything. Let me rerun this and try to see what is the gain over here. Can you see this is the gain now? So this is the gain what I'm seeing now. See now what is the gain? Gain happens to be, suppose if I just put it here, sorry, this should be on the green one. See what is the gain? So it is minus 827 millidBs. So this minus 827 millidBs corresponds to a magnitude of less than 1, which happens to be 0.909. So this is what is the gain you're getting. So this is the gain of this CS amplifier when I'm connecting 100 ohm to this amplifier, which had a gain of 10, so this is a huge reduction in the gain the moment I connect the load, meaning CS amplifier is unable to drive a load of 100 ohm with the gain what it had earlier had. So earlier it had a gain of 10. The moment I connect 100 ohm resistor, the gain has drastically reduced. Of course, it has got a valid reason. This effective load resistance has reduced to a very small value. Naturally, the gain won't reduce. So then what is the solution? The solution is, now CS amplifier is now cascaded with CG amplifier without RL. So what we'll do is, we will have this CS amplifier, we will have a CD amplifier followed by this CS amplifier. Let us take out this RL from CS amplifier and then put it after CD amplifier. Sorry, this is actually CD amplifier. So sorry for that. This is actually CD. This is, sorry. So this is actually CD amplifier. So now when this is CD amplifier, so now let us see what happens. Now what is the CD amplifier requirement? Okay, excuse me for this. This is not CG. This is CD amplifier. This is CD amplifier. So let me just bring down here. So now what are the specifications of the CD amplifier? So I have to have an input impedance far greater than 200k. Okay, anything greater than 200k is fine. So let me assume a GM of this second MOSFET or second MOSFET as 10. So let RS be 500 ohm. With these specifications, so with an idea of 1 milliampere, I need a WBL of 25,000 for this M2. So this is the required value of WBL. And if I solve theoretically, the gain of this amplifier comes out to be 0.98. That is the gain of this individual amplifier. If I connect the input here, if I take the output here, the gain is 0.98. So what I'll do now is, what is the advantage of having this amplifier, CD amplifier, as the subsequent stage after your CS amplifier is the input impedance of this is 204 kilo ohms, which will be connected as the load for this CS amplifier. So now when you're connecting such a high input impedance to this amplifier, the gain reduction will not be not that much. So the gain will not be reduced too much. So that's what is we are having now. Okay, to have an input impedance of more than 200 kilo ohm, so I need to, of course, upon designing, we'll get the value of R1 dash as 400k and R2 dash as 418.18 kilo ohms. So upon having the CD amplifier with all these specifications, now this is what I'm having now. Can you see now? This is a CS amplifier with a gain of 10. So this is a CD amplifier with a gain of some 0.98. So this is the gain. So when I cascade both of them, so I have to get a gain of, how much? So 10 multiplied by 0.98, which happens to be minus 9 point, of course, 9.95 is the gain of the amplifier. So if I just go back to my simulation, try to do it. So what we're trying to do here is, I had a CS amplifier with a gain of 10. I'm designing a CD amplifier with a gain of 0.98. Now I'm connecting the output of CS to CD. Now the overall gain is the gain of CS amplifier multiplied by the gain of the CD amplifier. So naturally I'll going to get, let me just go here and then let me connect this now. So what I'll do, I will actually now do the connection of this. So I will connect a wire from this to this, and I will open this, and I will certainly open this. I will not connect this, and I will not connect this also for the time being. I will not connect this also for the time being. So I'm not connecting this 100 ohm. So I'm having this as, okay, this is my connection now. So if I run it now, so now, okay, what was this? This was supposed to be 500. This was supposed to be 500, and I have to have, this is my, okay, 25,000 is my W bell. So now if I run this, you can see how much is the gain you have. You can see the gain is almost close to 20 dB. So how much the gain you have? The gain that you have is, okay, let me just put it on the blue. Okay, let me take out everything. Let me rerun this. Let us see what is the gain here. Can you see the gain of, can you see the gain which was reduced, which has actually reduced from, sorry, I have to put it here. Can you see the gain is now almost 19.97, which has actually increased from, okay, when I actually connected this without this 100 ohm, the gain was 20 dB. When I connected 100 ohm, it has come to minus 800 and something milli dBs. So the gain has reduced drastically. Now what I've done, so I have taken out this 100 ohm, connected a CD amplifier. Since the input impedance of the CD amplifier is, okay, sorry, this need to be, okay, let me connect that value. What is the value? It is 448. So let me just go back to my simulation. This is 400 and 418k. So this is 418k. This is 418k. Okay, this is my R2 resistance. So now the moment I just have this one, the input impedance is in terms of 200s of k. If I run it, you can see now I have a gain of almost, the same gain is retained back. So the gain is now again 20 dB the moment I connect this CD amplifier as the load for this, because this has got a very high input impedance of 200k or 204k. That's what we saw here. So the gain of the, You can see this is the input impedance of the CD amplifier. This is coming in parallel with 1K. So where the load resistance comes very close to 1K. So it may be around 995, something like that. So that's why the gain is not reduced. That's why the gain is not reduced. So now we'll just proceed to see what happens next if I connect RL. So you can see I have not yet connected RL now. The moment I connect RL, now, so the moment when I connect RL, so gain which was how much? So gain is actually 90. This is my input. This is around 19.95 dBs. When I connect this 100 ohm as the load, if I run it now, and if I see this output, so I will take out all these things what is that I have. So let me take out this, also. Let me see what is this gain I have. So this is the CS amplifier gain, which is okay. What is the gain of this? So this gain is 19.95. This is CS amplifier gain. Let me see what is the overall gain. So overall gain is now 18.97 dBs. So that's what we saw here. So now what we have actually here is this is the gain of your CS amplifier. This is the gain of CD amplifier. So what is the overall gain? The overall gain has now slightly reduced from 10 to 8.88. Its dB is 18.97 dBs. So this is the magnitude of the overall gain after connecting CS amplifier and CD amplifier, CS and CD amplifiers. So now what was the intention? The intention was to design MOSFET amplifier stage so that it will give a gain of 10 for a resistive load of 100. So we are almost there. So what we are almost there is we have a MOSFET amplifier stage comprising of CS amplifier and CD amplifier driving a load of, so this is my load. So what is the load? The load is actually 100 ohm resistor. Now the gain is coming out to be slightly less than 10. So that's what I have a gain of close to, okay, now I have a gain of close to of course this is minus 8.88. So I have to get a gain of 10 now. So instead of having RD of 1K, you slightly increase the value of RD from 1K to 1.12K. You'll get a gain of 20 dB at the final stage. So what I'll do here is I'll make it 1.12K. Let us verify what is the gain of the final state. That is, can you see now this gain is of course almost equal to 20 dB. You're almost there. So you could able to get a gain of 20 dB with the help of CS amplifier and CD amplifier, which is now cascading of CS and CD amplifier. So what is the need of this CS and CD amplifier is, the main purpose of CD amplifier is to make this 100 ohm very small resistance to look like a very heavy resistance, very high resistance at the output of your CS amplifier. So this is like, okay, impedance transformation. So impedance of 100 ohm will look like an impedance of almost 200 kilo ohms at this point. The input of CD amplifier is around 200k, which will not reduce, which will not load my CS amplifier. The moment when I connected only 100 ohm, the gain was hugely reducing because it was loading my CS amplifier. So instead of connecting 100 ohm directly to the CS amplifier, if I connect 100 ohm after CD amplifier, this 100 ohm will not be seen as 100 ohm here. Now this 100 ohm will be seen as something like 200 kilo ohms, which will not load my CS amplifier. When it is not loading, the gain will not reduce. The gain of this amplifier will not reduce. So since it has got a gain very close to 1, so this multiplied by this, you're going to get a gain of whatever that is intended. So you're getting a gain of 10 in this particular example. So you could able to drive a 100 ohm load using amplifier stages, which is cascading of CS and CD amplifier. CS and CD amplifier. That's how. That's where in usual circuits in analog electronics, whenever you're driving less resistive loads, or whenever you want to deliver larger current, it is not possible to do it using only one stage. So you have to consider cascading stages, because we need to have the output impedance of overall amplifier should be as small as possible. So that will be achieved using this CD amplifier. If you actually see what is the output impedance of the CD amplifier, it is very less. So that's what is an ideal amplifier requires. And of course the input impedance of this overall amplifier is close to around, okay, how much is this? Okay, 100 in parallel with 200 comes out to be, let me just find out, I think it is 66.66 kilo ohm, which is not bad. So of course we have 66.66 kilo ohm as the input impedance for this, and output impedance is not very bad. Now it is 1 over GM in parallel with, okay, 500 ohm is the output impedance, which is very less. That's why it is going to have a good transformation of the gain which is required for your circuit. So the parameters of these two amplifiers or these two MOSFETs can be seen here. Suppose if you do .op of this, so if I just, okay, do the simulation command edit, if I do only .op, you can certainly see, okay, I will run this. So you can see different parameters of this MOSFET, like what is ID. You can see ID assumed is 1 milliampere, it is flowing in both of them. VGS, of course VGS is as per your R1 R2s. Can you see GM here? So GM is, okay, in the first case it is okay, 10 millisiemens, and yes, in the second case it is 100 millisiemens. So that's what is our assumption. If you just go back to your slides and see, can you see this is GM2? So it is 1 over 10, so it is 1 over 10 is actually 100 milli. So this is what is 100 milli is GM2. So when it come to GM1, it's actually 10 milli. So GM1 is actually 10 millisiemens. So that's what we have. You can see this is 10 millisiemens and that is 100 millisiemens. So that's what is there in our simulation also. Can you see this is actually 10 millisiemens. So 1 exponential minus 2 is actually 10 millisiemens. So this is 100 millisiemens. So we have this much GM1, GM2, which is as per our design, and we have the corresponding RS and RDs. So we got a overall gain of very close to 10, So this is how you can able to design a cascade amplifier, which is CS amplifier followed by CD amplifier. This is common drain amplifier. Thank you.